This class number 26th of March 2020. We finished the Q element and told you already that the Q element is actually very useful. The interpolation in the Q element is better than the triangular element that you're gonna see today. So the Q elements generally used for the larger mesh than the triangular element in order to, it could be a cost-saving approach because you might not need as many nodes as the triangular element needs because the interpolation function for the Q element allows you to simulate the displacement profile more accurately, as it allows the nicer function to be used. But still, it is more expensive when you discretize everything down into the smaller size. You can see already that when we perform the coding for the Q element, you have seen a lot of activities. So you have the loop over the element to the number of elements. You finish that loop. Inside each loop, you're gonna have the loop in the integration point. At each integration point, you evaluate everything. You evaluate, at each integration point, you first come up with the C and eta associated with the integration point, and then you use the C and eta and substitute them into the derivative of shape functions calculation. You get Jacobian of transformation. You get dx, dc, dc, dx, or whatsoever. You get all of that, and then you bring them out to the B matrix. You get them into the B matrix. That's the B matrix evaluated at just a single integration point. So that B matrix is evaluated. You get the B transpose dB multiplied by Jacobian of transformation multiplied by the weight in both directions. And then you accumulate that evaluations up to the number of integration points you have. Then you get the stiffness matrix of one single element. Okay, so that is how it works for the Q element, and you can see the cost. That's my point. When you deal with Q8 and Q9, you can imagine how much effort you need to give in order to come up with the stiffness matrix, as you have 3 integration points in each direction. So you have to do all of that for 9 times, which is a lot. Okay. So basically, the T element is a cheaper one. But the cheaper element like T element gives us one bad thing about it. One thing that we may not like about it if the discretization is not done well. Or let's imagine if you have a very coarse mesh. The point is that the triangular element is gonna be not that option for you. So okay, triangular element. In the finite element analysis software, they call it T element. So this one we are talking about triangular 3-node element. T3. 3 stand for the number of nodes. We call it constant strain triangular, or CST. Sometimes it is called this way. Okay, so I would like to plot something. We are having the x and y coordinates. So the vertical direction here gives you the magnitude of whatever value you want, like the magnitude of displacement u, magnitude of displacement v, whatever. Okay, just the axis that represent the magnitude. So I just going to draw the element, which is the 3 elements over here. We have 3 nodes. Okay. So this triangular element here just stay on this plane, the x and y plane. Okay, it does not pops up in vertical direction because it is not the 3D problem. We are dealing with just the 2D plane problem. Let me get something from here. Okay. So, and we will show the profile or the plane of the values of anything at the associated node. Okay. So it could be the displacement, I told you, could be the displacement in U, in V, any distribution. So the value at each point are given as you can see now. And then we will be able to construct the plane of the few values. So I can draw the line like this. So just assume that we are talking about the displacement along of each node along the y direction. Then it is given in the following format. So the domain of the triangle is given by this omega subscript e. Okay, just the sign that stands for the domain of it. Each node you have the coordinate x1, y1. This is the known value, x3, y3, and the last one is the x2 and y2. So the associated v values are given by v1, v2, and v3. So the node numbering still follows the sign, the direction we had like before. We are running the node number along the counterclockwise direction like so. Now move this. So you can see here the interpolation on this plane. You have just 3 nodes. So the interpolation function would supposed to be only just the linear function. You just be able to constitute a straight plane. So the linear interpolation function for displacement over the domain omega will be given in terms of x and y coordinates. In the following. So the v, okay, it could be u, it could be v, it could be any function. It's given in terms of x and y. It's equals to a1 plus a2x plus a3y. So this is just a function that describes this plane. Okay. So at any point in this plane here, I'll just try to illustrate the plane. I'm not sure if it is a good illustration or not. So any point here, this is the v x y, which is given just on here. So the v function here contains the unknown constants, right? Thus, the following relationship if I substitute the xy by this, or even further to 2, what you're gonna end up with is the v1, v2, and v3, right? Because v1 is calculated from the x1, y1, likewise for v2 and v3. So I just write this out. v1 is equal to v x1 and y1, and it is equal to a1 plus a2 x1 plus a3 y1. As they are on the same plane, a1, a2, a3 are identical, and that is going to work for this and this. So you just simply drop in the x and y coordinates in place. Now, if you look at this picture, if you look at these sets of the system of equation, you find that we can write it in terms of the parameters, constant parameters a1, a2, a3, and multiply to the coordinates. So I'll show you here. This is, if you take the a1 out of this column, then you're gonna have just 1 left behind, right? So you're gonna have 1, 1, and 1. If you take a2 out, you get x1, x2, x3, and likewise y1, y2, and y3. So that is actually multiplied by a1, a2, and a3. Now the video for the last class FEM was uploaded. That includes the afternoon session. So I combined all of them into just one video for the morning and afternoon session and uploaded. So it is like quite long. It is 3 hours. For steel, I also uploaded. I processed all the video already, so I actually uploaded, but I'm not sure if the latest one is turned public yet already or not. But for sure, the one that the class on Tuesday was already public. Yesterday class, I don't remember if I make it public already or not. But to make it public, I just need to wait for the HD to be available, and then if you can watch the HD, then I turn the public on. So this one is going to be processed and try to upload it as fast as possible. Is that V1, V2, V3? Which one? Which one, Milk? Is that V1, V2, V3? What is that? You mean this, right? If you mean this, yes. Oh, whoa. Above? No. Oh, thank you. Okay. Okay, great, thank you. And now, okay, we get it. So in order to get the constant This is the known, right? As you discretize the for the structural element, the match, then you all know x1, x2, x3, and likewise for the y. And you will need to know this. So, in order to do so, we switch things around. Equal to multiply and inverse. So we will know the parameters a1, a2, a3, and then if we want to perform the inversion, first of all, the area. The area of the triangle is given by A is equal to the absolute value of a half. This is in your high school class. So if you recall, x1, y1, x1, y2 minus x2, y1 and plus x2, y3 minus x3, y2, right? Plus x3, y1 minus x1, y3, and this is it. We take the absolute value. Okay. So we perform the inversion of the matrix. We come up with the A1 being 1 over 2A multiplied by V1 x 2y3 and x3y2 plus V2 x3y1 minus x1y3 and V3 x1 y2 minus x2 y1. What? Okay. Fight with iPad. good note. Okay, get the A1. Now A2 is 1 over 2A, just like before. Should copy. Sivaram has comment, sir, if we divide one element and then put coarser mesh one side, fine mesh one side, there are more nodes not connecting each other. Wow. Do you mean triangular element or what? I don't think that you are talking about triangular element. Are you talking about this? Q4, do you mean that, Sivaram? But I think maybe it is not relevant to this thing I'm talking about now. I continue first. V1 V2 Y3 minus Y1. Okay, Sivaram, then I'll keep your question to the last thing. Okay, after we finish up this talk about the triangular element. Okay. And plus V3 x1 y1. Oh, okay, x1 y2 minus x2 y1. For A3 V1 times x3 minus x2 plus V2 when I edit the video, if I have time, I try to clear out my clearing throat sound. If I don't have time, then it was included in there. It is quite annoying to me, and of course it's gonna be annoying to you, I know. It's still there. Got to take probably mucosolvan, like mucus relief in the throat. Let me check. A1, B1, x2, y3, x3, y2, and B2, x3, y1, x1, y3, and x1, y2, x2, y1. Okay, looks good. For A2, 1 over 2A, V1, y2 minus y3, v2 y3 minus y1, and y and v3. Oops. This one is incorrect. Y1 minus y2. Okay, for A3, V1, x3 minus x2, V2, x1 minus x3, and V3, x3 minus x1. Looks good. Now, substitute A1, A2, A3. into the vxy we had in the page before. So v x and y is equal to a1 times a2x and plus a3. Okay, so start with the a1. Lucky that I have the iPad. This class used to be very laborious, writing things quite several times. So the A1 is in place now. Then it is added up with A2 times x. So first of all, as they are sharing the same common 1/2a, I start the bracket over here, and then the rest of the thing will be inside the same bracket. I'm gonna remove the end bracket over here, and then we have a plus x multiplied by things inside A2 plus y okay. And then we finish it up. Close the bracket just like this. So you are sort of like fascinating. So how is this going to be useful? The point is that if you look at this expression given, you will be able to group things in the following. You have v1 and then the terms here multiplied by v1 and the terms here multiplied by v1. Next, things in v2, you can group them up and you can group them up this way, and same for the v3. So if you are able to group up terms, we have v1. v1 is the nodal point value of your displacement. We talk about displacement first. So you take the nodal point value of the displacement and then you multiply by some sort of function, as it includes constants and also the x and also the y. We're gonna call it function phi1. The phi1 is given by the function of x and y. Plus you have the v2 as well, so you have the phi2, the x and y, plus the v3 and phi3, x and y. Now let me ask you, do you see anything? The function phi1, phi2 and phi3, they are multiplied to the v1, v2, v3. So basically all of these serve like the interpolation function. And then we will write them out. So starting with the V1, it is given by x3 y3 minus no, it was supposed to be x2 y3. How do we get it? x2 y3 in here minus x3 y2 plus you have the x here, right? X multiplied by y1 y3. Oops, y1. And then plus the y multiplied by x3 minus x2, all divided by 2a, because you have the 2a out there. Okay, and then we move forward. So for the shape function number 2, you have x3 y1 minus x1 y3 plus x y3 minus y1 plus y, and you see x1 minus x3 divided by 2a. The third one, x1 y2 x2 y1 plus x y1 minus y2, right? y1 minus y2, yes. And plus y x3 minus x1. Why? Seriously? x3 minus x1. I think x2, right? Where for y okay, it is supposed to be x2 minus x1 here. That is x2 minus x1 divided by 2a. Okay. Now, do you see the beauty of it? If you start seeing the beauty of the derivation, the shape function is given already. Let me bring you further. The expression for strain. If you recall, it is equals to partial derivative of u x, right? Partial derivative of v with y, and partial of u y plus partial derivative of v x. So we can come up with the B matrix. So the B matrix we are dealing with for now. I shall show you the picture for visualization just a little bit. You have the triangular element. At each point for the plane problem, you have u1, v1, u2, and v2. You have 2 degree displacement degree of freedom at each point. That makes your displacement of okay. We have in total 6 total point displacements in X and in Y. So, knowing that, the partial derivative of u with respect to x is going to be partial derivative of phi1 with respect to x multiplied by u1 plus in what line, what is that, x y2 minus y3 phi1, you mean phi1 x times y2 or y2 minus y3. Okay, yeah, thank you. Oops. y2 minus y3. Thank you. And then add up okay. So it's gonna look like this for the Q, for the T element, and for the derivative of U with respect to X. We have 3 pieces over here. Now, this is where you will see the beauty of this formulation. We have derivative of phi with respect to X. Previously, the formulation was made in the local coordinates. Now, the shape functions you have here are made in the global coordinates, or the physical coordinates, X and Y. So, if you want to find this quantity, it is very easy. So you take derivative with respect to X. So just this term inside survive. So I am going to put all that in. So first of all, we have y2 minus y3 over 2a, 0. The next one, derivative of v with respect to y. Okay, so displacement v, then this has to be 0. And with respect to y, so you get x3 minus x2 divided by 2a. Okay, which is taken from here, x3 minus x2 divided by 2a. This part here, constant, will not survive because we take derivative, they will not make it. So we can look at to just these 2 columns. Last one, x3 minus x2 divided by 2a, and another one, y2 minus y3 over 2a. That's it. Next, we move to the second node. So for the second node, derivative of shape function with respect to x, you get y3 minus y1. And then we get x1 minus x3. Okay, let's squeeze it in a little bit to make more space. By the way, what is going on in the other classes? So using Zoom or using something else, AIT share. Last one. For the third node, you take the derivative of shape function number 3 with respect to x to have y1 minus y2 over 2a and 0. And with respect to y, you get the x2 minus x1 over 2a. Okay. So this is very easy for the implementation. It is a cheap element and it is very easy for the implementation. So the coding is going to be really easy. Okay. So let me expand this here to make sure that you still catch up with the content. Derivative of v with y is given by partial derivative v1 with y v1 plus partial derivative of v2 with y v2 plus partial v3 with y v3. And but the partial derivative of u with x with y plus partial derivative of v with x is going to be given by I keep this there for time being. Don't want to write, so switch it around. Add up, and then the we're supposed to we're supposed to be following the order in the B matrix. So here's the thing: partial phi with y1 times u1 plus partial phi 1 v with x. Okay, and then with y come in, with x going to come in as well. This is with U2 and V2, and then with Y that is taking this and V3. Okay. A long one. This explains everything. You have the B matrix well constructed. So what is going on inside the finite element code? You will have only the for I equals to 1 to NELE, and then inside that you just need to take the temporary xy coordinate of a given element, and then you use these xy coordinates plug in to the known xy values over here. You do not have any constant x and constant y. No, you don't have any variable x and y anymore in here. You can see that x2, y3 they are the known. x3, y1 are known. Everything is known, and area is also known. So make a remark here. All entries are known values. That's a good thing. So we can come to the next page. That the matrix stiffness matrix is given by integration of this domain B transpose D and B dx dy. You know that the problem, the issue that caused us to get into the numerical integration is because we really need to conduct the integration. But over here, inside the B, known constant, D is also the known constant, and another B is also a known constant. So in that I can take the B transpose the B out of the integral, leaving this inside. What is this? This turns out to be the area, right? You integral over the domain, your triangular domain, and what's left inside the integral is just 1. So you end up with just the area And if you end up with the area, you can come back to here and then you take the B matrix here. No, don't. But yeah, you can take the area out, but as you have the B matrix times B matrix, so you're gonna have 1/2A twice. Yeah. Delete out. Okay. So you might have just this 1/, let me call it the B star. Actually, we don't really need to do it. If we don't want to, we just let the computer does its job. So this is also like 1/4A B star transpose D B. We have just a little easier form of the B star than the B, but just a little bit. So you in the implementation in the code, then you don't need to put a lot of 2A under as a denominator. You just pull them out and perform the calculation. For here, I subtract with the A we have over here already, because this is A, and basically before you have 1/4A squared, right? And A cancel out, so you have only just 1/4A. B star transpose the B star. That's it. We are going to continue over here. I think I need to come to the plane, and I need to open up the some main. I can take the main 4. I will modify this, so I save as main triangular. Actually, I should not forget what Sivaram asked me. Okay, so the main triangular here, we're gonna make modification from the code we used to have before, and we need to clean out a lot. We also need the triangular mesh as well, not only just the change of the core in here. So I clean out this core, okay? It is not going to be usable with the triangular element, as this one is for the Q element. But anyway, the KELE, if we go like this, I am just thinking of if it is possible to just add it into the existing code, and then we have one code that is capable of running the analysis that includes both the Q and the T element at the same place. That is also possible, but for each element it has to be declared that it is what kind, the T, the Q. The part over here we can come back later because we're gonna need the match. If we match it already, then we need to put the boundary conditions, the node number, apply force, and many things to do. But for a time being, we can start over here. So KELE, this is for these structural elements, and the size of this matrix is going to be 2 times element type, which is going to be 3. So we're going to have the 6 by 6 matrix. So this is going to work. E, X, Y, Z is the temporary coordinate of that element, and it is taken from the size is 3 by 2 for here, so it is going to work as well. And over here we have the part of the code that migrates the XY coordinates from the mesh we had into the EXYZ. So this is going to work as well like before. So the part that will not work will be the loop over the Gauss point, because we have nothing to do with the Gauss point anymore. So from here to here, then I just clean it up, and you're gonna find that it is unbelievable that the code is super short to make the the triangular element. So underneath this point here, the B, let me undo a little bit. I just want to see if there is the chance to merge the code for the Q and code for this. So okay, the B is assigned over there, then I don't keep it. It is assigned inside the operation within the integration point, and it is not convenient for this purpose, for this case. So I'll put it this way. I put the if over here, and we know that okay, if the element type is equal to 3, then the B matrix is going to be zeros. What is the size? We have 3 rows, and 2 multiplied by E type. Actually, this is universal, but as it is within the E tip, then you waste the time. So just make it 2 by 6. Now we have the B matrix allocated. I'm gonna put the NF over here. Okay. So B matrix, the first one, we take the B mat equals to, this is a B mat star. I think it is easier to code this way using the B mat star. Then B mat 1, 1. How many do we have? We can come back here to check. So we have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So come back to that screen. 12. Number of column, I'm not putting it in there. B mat row number 2 and leave the column there. and B mat row number 3 equal, and the same thing, and that is going to repeat. So as a matter of fact that you just need to just repeat this for 12 times, well, for all 12 entries. So the formulation are different. Okay, so start with the BMAT 11. What? BMAT 11, 22, 31, and 32. 1, 3, 2, 4, 3, 3, and 3, 4. 1, 5, 2, 6, and 5 and 6. That's it. Now, you take the first one, y2 minus y3. And the next one, x3 minus x2. Let me see if I can add some sort of the screen while I'm shooting the video. So I will add the where is it? Video capture device and Live Gamer Plus. Yes. Okay. Okay. It doesn't pick video capture device. Yes, but it doesn't pick up. Fine. I switch around to screen then. Okay. So come back to here. y2 minus y3. So y2 minus y3, it comes from exyc, comma 2. This is for y, right? y2 minus y3. y3 is for the node number 3. This is the node number 2. That's it. The next one, x3 minus x2. If we talk about x, then the index here is changed to 1. x3 minus x2 is going to look like this. And then this is equal to b mat 2, and b mat 1. That's it. Yeah, simple. So next I have y3 minus y1 over here. So copy and paste y3 minus y1. Next, it is x1 minus x3. x1 minus x3. And then b mat 2, 4. And then b mat 1, 3. Next one, again, copy and paste. It is y1 minus y2. Next, x2 minus x1. And then b mat of 2, 6. And then b mat 15. That's it. The plugging in routine, let's look at it. This is usable, right? Because these range from 1 to 3, 1 to 3. And for each cell, you have in total four blocks, four entries. So this is going to work. So this will be all for the implementation of the triangular element. And in fact, you can just put some part over here. This is for quadrilateral elements. So it is turned off over here, but you can just add this part into the main code we had in the previous version. But again, if you want to, you can play with this further. So you just need, instead of E type, the element type here, we just use one variable, and this is universal for the whole calculation. If you have the mixture, then instead of using E type as just one number like this, E type has to be the matrix, and it is going to be associated with the individual element, and from that, E type will be controlled by the index I. So you will be able to use many sort of structural elements in one place. Okay, E type is done right now. What is the next? We need to come up with the node. So the mesh. So I keep it, save it here. In order to get the mesh, well, we look into QRect mesh. This is for the rectangular mesh Q4, Q8, Q9. Yeah. If we want to mesh it into the triangular element, let me see, what is that LBL? Axis equal label. Okay, it's just the condition to turn on or turn off the label of the axis of the node number labeling. Should we I just make another subroutine then? QRect mesh. I'll make it rect mesh .m and remove the Q, because this is not for Q anymore. This is a new version that incorporates the triangular element as well. So we use the if, else, if, right? Else if E type is equal to 3. X, Y coordinate, how many X and Y coordinates do we have? It's going to be identical to this one, to the Q4 element, right? The thing is that you don't need more nodes than Q4. You just have the triangular shape. It looks just like that. So N map, the mapping is going to be twice as much of the Q4. So in one block of Q4, then we can break it into two pieces of the triangular element. So N map is equal to 0, 2 times nx times ny, comma, e type, which is 3. That is going to work, or I make it 3, not necessary to keep it that way. Okay, so first of all, the part here is generating the xy coordinate. We can just copy from here because the nodes will be identical to Q4 nodes. Okay, so we copy, and then the part here for the nx and y here. Okay. But wait a minute. We are going to have the double number of the mesh. So better. Well, yeah, this is a lot of headache, right? But okay. Come back to here first. Let me switch the screen. Mesh looks like this. Oh, this is so sleepy for me. Driving back and forth and then start the class, the energy is not quite high. Do this. Okay. And what disconnection? And for one element, you're gonna have this first, and this, and this, and this, and so on. So if we have the node for Q4, it is easier to just pick the node from Q4 and then we just rerun the node. So in here, we need to have the new N map. N map, we have I minus 1 times nx. It is not going to work this way, so it is going to be 2nx, 2 times nx. Let me do it in a different way. N map I minus 1 multiplied by 2 times nx plus j, not just j, but it is 2j. 2j or 1. J is 1, 2, 3. Okay. But if it is like this, then 2j minus 1. So if we are, oh sorry, I didn't switch the screen back. So if we are at the what? Let me check the screen. Okay, if we are at the second column, I is equals to 1 minus 1 minus 1 turns out to be 0. Okay, so you have the part here 0, and then 2 times j. So 2 times j, your j is actually equal to, for this, it is equal to 2, right? So 2 multiplied by 2, you get 4, and then you minus 1, you get this element, and without minus 1, you will get this element. So we are talking about the left element first, so 2 times j, and then minus 1, comma 1. Two, 3. And for another element, we'll be picking this up and just use this code. And now look at this. This is the first node, second node, third node, fourth node. Come back to this screen. So first node is this one. This is how we set up the node. And here, the first element is supposed to get 1, 3, and 4. The second element will be 2, 3, 1, or 1, 2, 3. So we come back to this one here. 1, 3, 4. What is 1? 1 is this one here. 3 and 4. Okay. And the second one is 1, 2, 3. Now it is useless, then delete. Okay, well, we get right now the Nmap. This is a construction of Nmap, and there it is, the construction of the XY coordinates. We get all of these constructed, then we match, so we can I just draw the match. For I equals to 1 to size of Nmap, which is in the first one, number of row. Number of row, identify the number of element, right? And then I will get the XY coordinates. Okay, this is a good one. You can copy from here and paste it there. So if so, I migrate the coordinates into the temporary one. For K, I need to assign first the E X, Y, Z is equal to 0, 4, 1. Format indent code. Okay. We plug in the K. Okay, now we have the J too. We cannot use it just right away. K equals to 1 to 3. I fix it to J then. And J, XY co N map of, I don't use this, I use just the I. And K, okay, now we change it to J, right? So we transfer the XY co at the node J, at the node local node J, from the global node there, and then the E type plus 1 just replace by 4. We waste of time calculating 3 plus 1 equal to this, and plot this, and that should be it. N4 axis equal N4. That's it. Oh, not N4. No, not supposed to be. It is like an if. That's it. Save it and call it. It's supposed to work. So rect mesh element type replaced by 3. NX make it 5, NY make it 4, HX 2, HY 3. Error. What? N4. What is that? Line 1 near column 25. Line 1. Where is it? What is N4? Can I see it? Error. N4 undefined. Ouch. Okay. Other error. Line 30, column 16. This should be easy. Line 30, column 16. What is the complaint? Non-conformant argument, column 16. Column 16. XY core non-conformant. Okay. It was supposed to be 2, sorry. That's it. Why does it take time? It takes so much time to just mesh this. Why? What is going on? Oh, too much time. Gosh. And okay. It does not. I don't have the hold on. So draw the mesh. Where is it? Hold on. Okay. But it takes so much time. It is so slow. Okay. Right. Now we have rectangular mesh. We are ready to perform the calculation out of this one. So we have the mesh, we have XY coordinates, we have N map. We feed this information about the mesh into the main code, and we be able to perform the calculations upon the use of the triangular element. Okay guys, this is 10 o'clock, 10 minutes past 10. So you will get ready for earthquake engineering, which is coming up next in 20 minutes.